Hi, this is our formal lab number 2, making Play-doh circuits, by Maria Berry, me, Philip Longueuil, and William Wooley. In this lab, our main goals were twofold: to collect the data required to solve for the resistivity of Play-doh, and to determine what kind of circuit, series or parallel, would allow things to still be successfully powered while in a circuit with this resistor. Our overall question was this: how can we incorporate a functional Play-doh resistor into a classical circuit so that a light bulb and fan in the circuit can operate? After building a circuit with our homemade Play-doh resistor, which we found to have a resistance of 2,540 ohms, we determined that putting our resistors in parallel to the rest of the circuit created a better functioning circuit, as would maximize the amount of voltage and thus power each circuit component could receive. This is because, since there was less voltage drop across the resistors, less power was dissipated. To test the resistivity of Play-doh, we created a circuit. A circuit is a closed path in which electricity can flow as current. Circuits can consist of multiple loops or multiple pathways that electrons can take to distribute electricity to multiple components of the circuit, such as resistors, which reduce current flow by dissipating electric power. If two resistors are in parallel, they are in two different loops, and the current running through the system will be split between them. In this lab, we created a parallel circuit. If two resistors are in series, however, meaning that they are in the same loop, the voltage will be split between them. Voltage, in simple terms, deals with electrical potential energy. It is the push that makes electric charges move. In other words, it is the difference of the number of electrons between 2 points, in combination with the potential for these electrons to equalize themselves. In our circuit, there was another resistor in series with the Play-doh resistor. We modeled our setup in 2 ways, a circuit diagram and a power box. We found this setup worked the best to make the light bulb light and the fan run at the same time. We also used the voltage of the batteries and the resistance of the circuit components to find current through each part of the circuit. In the case of the resistors in parallel, it is likely that they worked like a voltmeter, meaning little to no charge passed through, as less than 0.005 amps of current went through that section. One issue with our model is that Play-doh is a sphere, and the equation we use to calculate its resistance is best suited for cylinders, so this reduced the accuracy of our calculations. An assumption we made during this lab was that difference in shape would not significantly affect our results. Our experimental design revolved around the idea that resistors in parallel disturb the voltage difference less than those in series. Just as we know voltmeters need to be in parallel due to their high resistance, the same logic was applied to the 2 resistors we needed to incorporate into the circuit. This idea was supported by the data, because when we changed the resistors to be in series with either the other components, the bulb glowed dimly or not at all, and the fan did not start. The resistance of the Play-doh circuit that we made can be found by multiplying the resistivity of Play-doh as a material by the length of the resistor we made from it, and then dividing this by the cross-sectional area of the resistor we made. After this, the electrical current that is passing through that resistor, which is also the current that is passing through that loop of the parallel circuit that the resistor is on, can be found by using Ohm's law. The voltage of the battery in the circuit is divided by the sum of the resistances on that loop in the parallel circuit. It was found that the current running through the loop which contained the Play-doh resistor and the normal resistor was 1.603 times 10 to the negative third amps. It makes sense that this value is so small, since the resistance of the Play-doh resistor is so large, meaning that it dissipated a lot of power. Because the resistance value of the Play-doh is over twice that of a resistor, this means that our resistor made from Play-doh is better at resisting, or opposes more current flow in the circuit. This may not be true for every resistor made with Play-doh, however. Additionally, there is some error and uncertainty in our experiment. The resistance value we recorded for the non-Play-doh resistor, 1200 ohms, was from an outside source, as we were unable to determine it during the class period. This possibly inaccurate value could cause error in our data. These calculations would have also worked better with a cylinder-shaped resistor, as opposed to a sphere. In conclusion, when designing circuits, it is more efficient to put the things that are being powered, such as a light bulb or a fan, into a parallel circuit. This is because the overall resistance of a circuit with multiple resistors in it will be much less if the things with resistance are in parallel than if they are in series. This is why, in spite of the enormous resistance of the Play-doh resistor that we had in the circuit, the light bulb still lit up and the fan still spun. Overall, resistors are less able to dissipate the power in a circuit when put in parallel.